And this one is this time. So what we want is the derivative of the function that is the inverse for the restricted cosine function. So if we have y equals cosine to the -1 of x, basically the inverse cosine notation that we have for inverse cosine, we agreed we're a little bit more comfortable with the cosine to the -1 than we are with arc cosine, so I'm good with that. It goes, just depends on the textbook, which notation that you run into. We want dy dx. So if we want to find dy dx, what we're going to do is we're going to, the plan is find dx dy and use the fact that dy dx is actually the reciprocal of dx dy. That's the plan. And it worked pretty well last time. We're going to try it again this time. So if y equals inverse cosine of x, we're going to observe that x equals the cosine of y, at least the restricted cosine of y. And then it's very easy to find dx dy. If we differentiate both sides with respect to y, it's d dy of x equals d dy of cosine y. d dy of x is the derivative of x with respect to y, and the notation that we would use for that is dx dy. d dy of cosine y, since the variables match, the chain rule really does not come into play. It's just negative sine y. Just like that. So now if we use this fact, dy dx is 1 over that, we can say dy dx equals, I can say 1 over negative sine y. Probably I should, but what I'm going to say is -1 over sine y. Will you let me get by with skipping the step of transferring the negative sign from the denominator to the numerator? Okay, so -1 over sine y. The catch is, this would work, but the catch is that the expression was given, well, cosine or inverse cosine of x, given in terms of x. So the final answer needs to be in terms of x, not in terms of y. So we keep it going here, and we say, oh, I need room for my right triangle. Maybe I can draw the picture over there. This dy dx equals -1 over the sine of the inverse cosine of x. And if we write expression for the sine of the inverse cosine of x, then we'll be good. Now we could probably use y here, but I like just introducing a variable theta because we think of it as an angle. It just was more comfortable with me. So here's theta. And if we let theta equal the inverse cosine of x, basically we want to be able to take the sine of that. So think of it as an angle, think of it as taking the sine. So cosine of theta equals x. So I need to write this in such a way that the side adjacent divided by the hypotenuse equals x. So if we look at this triangle, and you just do basic right triangle trigonometry on it, sides adjacent divided by hypotenuse is x, and that's cosine of theta. What is the other side, the opposite side, then, in terms of x? Using the Pythagorean theorem, it's a square root of 1 squared minus x squared, or simply 1 minus x squared. So then we take the sine. So the sine of theta is equal to the side opposite divided by the hypotenuse. So dy dx equals -1 over, well, inverse cosine of x is theta. Sine of theta is the square root of 1 minus x squared. So that basically finishes it. dy dx equals the negative of 1 over the square root of 1 minus x squared. Yes.
Why couldn't you just go back to the sign, the step where it was the cosine of y equals x,
Mm-hmm.
and then draw your triangle and plug in cosine is x over 1, and then solve it like that?
Maybe. Which step is it? Right here?
Right.
Well, we first need to find the derivative. If we did that first, cosine of y equals x, angle, what would that look like? Cosine of y equals x over 1.
And then get
At some point, we would need to find the derivative. See what you're saying there. Cosine of y. The angle is y. That kind of makes sense. I think I might just have to give that some thought, because it wouldn't feel right to bypass the derivative entirely. At some point, we have to differentiate with respect to x.
But it wouldn't be negative either, would it?
I guess it would not be negative. Maybe that maybe it wouldn't necessarily get the same answer, and it's because we're not taking the derivative. Yeah, somewhere in there we have to differentiate. We need to come up with an expression for dx dy, and ultimately use that to find dy dx. Once we get to that point, then there probably are multiple ways of going about this. There's a formula way up at the top. Formula right there, ddx of f inverse of x equals 1 over f prime of f inverse of x. And just in practice, I don't really think that's as useful as 1 over dx dy. I've used that in the past, and it seems like 1 over dx dy works just as well. So that's the way I've elected to go with this. All right. Let's look at least one of these. We did ddx of arc 10 last time. All right, the dreaded arc sec then. Let's do that. I want to say this was also last time. So this is going to be this time. ddx of the arc secant. Now one approach could be to write the arc secant in terms of the arc cosine. Let me see how that would work. I don't think I want to go that way, but let's see how we would do this. What we have is y equals secant to the negative 1 of x. So inverse secant of x. And what we can also say is the secant of y, well, let me write it like this. X equals secant of y. X equals the secant of y. And we'll proceed kind of like what we did. If I want to write this in terms of cosine, we know that secant of y is the reciprocal of the cosine of y. So what we could do is we could say 1 over x equals 1 over, x, just plain old x, equals 1 over cosine y. I'm not taking reciprocals of both sides, I'm just observing that secant of y equals 1 over cosine y. Then what? We could approach this. We need to find ddy of both sides. It's just going to be a little bit. It's going to be a little bit trickier there. Is there some way? Oh, let's do this. Let's multiply both sides by cosine y and divide both sides by x. So would it be correct to say that y equals the inverse cosine of 1 over x? You think? Inverse cosine of 1 over x? And the advantage to that would be we already have a formula for the derivative of the inverse cosine. Negative 1 over square root of 1 minus x squared. So if we wanted to, we could use the chain rule to find the derivative of inverse cosine of 1 over x. That would be one approach. And if we had limitless time to talk about such things, it might be good to take both approaches and see if they get the same final answer. But, yeah, I certainly hope so. But that would be, it would just be a straightforward, we know a formula for the derivative of inverse cosine of x. We should be able to use the chain rule and find the derivative of inverse cosine of blah. In this case, blah equals 1 over x. All right, so maybe I won't go this way, but it's one possibility you might try. Let's go this way instead. Dx dy equals, okay, what's the derivative of the secant of just plain old x if we're differentiating with respect to x? It's secant x tangent x. So derivative with respect to y of secant y would be secant y tangent y. So I don't know why I had to think about it in terms of x, because there's no chain rule going on here. It's just secant y tangent y. Now, we need dy dx. So dy dx is the reciprocal of that. Dy dx equals 1 over secant y tangent y. Now, it might make sense to write this in terms of cosine, except that the y is inverse secant. So secant of inverse secant might be simpler than cosine of inverse secant. So I'm going to leave it like this, and what we need is to be able to simplify this. 1 over the secant of the inverse secant of x times the tangent of the inverse secant of x. Because y, after all, is inverse secant of x from the top. Now, provided, let's see, no, inverse secant of the inverse secant of x is going to be just plain old x. X really needs to be in the domain of the inverse secant function in order to be able to do that. But it will be. So that part's going to be x. The other part, we're going to need another right triangle. So for the right triangle, it's going to be theta. And theta is going to equal the inverse secant of x, and we want to be able to find the tangent of that ultimately. So the secant of theta is going to be x. And we could write that x over 1, but it turns out that it causes problems if we write that as x over 1. Because secant, what's the ratio for secant? Hypotenuse over side adjacent. Now, it's not a bad idea to let the opposite side be x or the adjacent side be x, but if we let the hypotenuse be x, when you think about when we do unit circle trigonometry, the hypotenuse is generally a positive number. The radius, basically, is going to be a positive number, positive 1 if we're doing the unit circle. So we would kind of leave out the possibility that x could be negative if we stick the x up there on the hypotenuse. So I'm going to leave the x, try to put the x on the adjacent side. So instead of writing it as x over 1, this looks a little weird, but see if it's not equivalent. I want the hypotenuse to be 1, and I want the adjacent side to be 1 over x. And I think this is going to help us when we get to what the domain of this thing should be. So 1 over x. That way x could be positive, x could be negative. So there's the 1. There's the 1 over x. And over here, this is going to be 1 minus 1 over x quantity squared, or maybe just the x squared down in the denominator. That's the opposite side. Now we've got to find the tangent of this. So the tangent is going to involve that opposite side. So it's kind of important. So the tangent of theta is equal to the opposite side divided by the adjacent side, which is equal to x times the square root of 1 minus 1 over x squared. We want to simplify that as much as possible, simplify the radical, simplify the fraction underneath the radical. So it's going to be x times the square root of x squared over x squared minus 1 over x squared, getting a common denominator there. And so that's x times, I'm going to skip a step here just because I'm short on space, the square root of x squared minus 1 over the square root of x squared. Is that okay? I skipped the step where I write it as the square root of the fraction, where x squared minus 1 is in the numerator and x squared is in the denominator. Skip that step. And then use the quotient property of radicals, and we get this. Now, here's the thing. What is the square root of x squared? Yeah, sometimes it's x. Yes.
Instead of all that, couldn't you just replace the 1 over x squared with x to the negative 2?
Maybe. Well, yeah, but I would worry about the negative exponent. Yeah, I want to write it in such a way that it doesn't have a negative exponent or a fraction underneath the radical sign. And I think this might be it would work. It would be equivalent, and if so, we could just leave it like that. I'm going to say it's x if x is positive, it's negative x is negative, but in any case it's equal to the absolute value of x. Square root of x squared is equal to the absolute value of x. So I'm going to write x over the absolute value of x times the square root of x squared minus 1. All right, so let me shrink this down a little bit and see if we can come up with a final answer. So dy dx equals 1 over x times x over the absolute value of x times the square root of x squared minus 1. Is this going to get us where we need to go? Dy dx equals 1 over x squared over the absolute value of x times the square root of x squared minus 1. Is it true that x squared always equals the square of the absolute value of x? Take a number, don't take the absolute value, then square it. Take a number, take the absolute value, then square it. Can we always get the same answer? Yes, whether x is positive or negative or 0, always get the same answer. So, could I do this? And then once I do that, I can divide out a common factor of the absolute value of x, and that'll give us this. This equals 1 over absolute value of x times the square root of x squared minus 1. Is the derivation of this? I don't think so. But what you will want to do is memorize. If you memorize 3, I think you get the other 3 for free. And let's see if that's the case. Buy 3, get 3 free. Yeah, it sure is. If you look at the derivatives of the inverse sine, inverse tangent, inverse secant, they are, as we showed last time, with inverse sine, inverse tangent, and this time with inverse secant. If you look at the derivatives of the corresponding inverse cofunctions, the derivative of inverse cosine is simply -1 times the derivative of inverse sine. And the derivative of inverse tangent is -1 times the derivative of inverse, I meant to say inverse cotangent, didn't I? Is -1 times the derivative of inverse tangent. And the derivative of inverse cosecant is -1 times the derivative of inverse secant. So if you can memorize the 3 on the left, and you can remember to multiply by -1, then you've got the 3 on the right. So hopefully it's less work here. Now example 7, what I'm going to do is very similar to what I was considering doing with the previous example. Arctan of 1 over x is actually equal to arc cotan of x. Should I go through that again, or is that believable? I think even if it's believable, I should probably go through that again. If we have y equals inverse tangent of 1 over x, then the tangent of y equals 1 over x, but then 1 over the cotangent of y equals 1 over x. When you reciprocate both sides, the cotangent of y equals x, but that means that y then is equal to the arc cotangent or inverse cotangent of x. So if we find dy dx here, what we ought to get is -1 times, well, not -1 times that, but -1 times 1 over 1 plus x squared. So here goes. I'm not going to go through the whole right triangle thing. All we have to do here is use the chain rule, because we're given that d dx of arctan of u is 1 over 1 plus u squared du dx. Or when you come to the test, you'll have this in your head and you'll know it. And so you'll be able to use this fact and apply the chain rule. So here goes. d dx of inverse tan of 1 over x equals, well, the derivative of inverse tangent of something is 1 over 1 plus that something squared times the derivative of that something. And in this case, it would be nicer to write that x to the -1, for sure. Because we need to apply the power rule to take its derivative. But that's the setup for this derivative. It's the chain rule, using this as kind of our template. It's 1 over 1 plus u squared. The u is 1 over x, and the du dx is the derivative of 1 over x with respect to x. So we work through it. I think I want to wait a moment before I do too much in the way of simplifying. Maybe write it 1 over 1 plus 1 over x squared. But I'm hopeful that something good will happen over here. This is d dx of, may I just scratch that and call that x to the -1? That should be okay, huh? You can look at that and say, oh yeah, that's 1 over x. Apply the power rule. -1 times x to the -2. Now you know what I want to do. I want to scratch the x to the -2 and call this -1 over x squared. Would you let me get by with that? Yeah, maybe. So here goes. That's actually -1 over x squared. Now, if you give me that, then we can get this one done pretty quickly, because I'm thinking about this as multiplying these two fractions, -1 times 1 up in the numerator, and then in the denominator, I'm thinking about distributing the x squared across those parentheses. It's like 1 over 1 plus x squared times x squared. So what I want to say is the 1 times x squared plus the 1 over x squared times x squared. And I want to get x squared plus 1 and be done. Just like that. Yeah, I feel like skipping several steps, but they were small steps. I mean, you could look at x to the negative 1 and realize, oh, that's 1 over x. And you can look at x to the negative 2 or 1 over x squared and realize, oh, that's x to the negative 2. But that's it. And compare that negative 1 over x squared plus 1. Compare it. Oops, sorry. I should have copied those and put them into the notes, but they're in these notes. Compare that to this. So just in case you're going by that, let me put those in there as well. All right. Hopefully there'll be another example in the review problems, which is pretty much where we need to go next. We need to look at the review problems from 3.6, 3.5, and 3.4, possibly in reverse order, because that's where the focus of the next test will be, and then we'll do 3.7 after we're reasonably satisfied with those. Let's see what this looks like. So homework and 3.3 through 3.7. Three 6, 3.5, 3.4. 3.3 was not on the last test, was it? Or was it?
No.
It was not. Oh yeah, okay. So we need 3.3 also. So 3.6. Not much to look at from 3.6, huh? That must be really easy stuff. Or maybe it's really difficult stuff. That's why I couldn't put many problems. So there are basically 5 derivatives to find. Which one is the difficult one? First one's not bad. It's just it's bad if you feel like you need to express your final answer in terms of x. I don't think that's going to happen. For that one, if y equals 2x to the 5th plus x cubed plus 1, the derivative of the inverse, well, we need to write the inverse. The inverse would be x equals 2y to the 5th plus y cubed plus 1. And I guess a better question would be, how do we know this even has an inverse? Do we know it's a one-to-one function? How would we know such a thing? Could graph it. Could graph it. Probably does something like that, and probably passes the horizontal line test nicely. Failing that, or maybe in addition to that, you could differentiate it and say dy dx equals 5. No, what's 5 times 2? 10. 10x to the 4th plus 3x squared. And, ooh, goodness. Now, x could be 0, but I think it's just 0 at 1 for when x equals 0. Otherwise, it's always positive. It's always positive. So, basically, when x is negative, it's going to be increasing. And when x is 0, it's going to have a horizontal tangent line. And when x is positive, it's going to be increasing. So that should be enough to conclude it's a one-to-one function. It's not constant on an interval, and it never changes from increasing to decreasing. It's increasing on its entire domain. So it has an inverse. dx dy equals 10y to the 4th plus 3y squared, and dy dx is the reciprocal of that. 1 over all that. Now the catch here, 1 over 10y to the 4th plus 3y squared. The disappointing aspect of this, of course, is if you want to know the slope of the tangent line and all you know is x, you have some work to do because you have to figure out what the y coordinate of that point would be, and that could be a difficult task. Okay, so hopefully not too bad there. Well, we just did a chain rule. We didn't do one with the inverse trig function on the inside, though. That might be interesting. Let's try that. Y equals the natural log of cosine to the -1 of x. Want to find dy dx. And this is a tailor-made chain rule problem. The outside function is the log. So what is the... This is the classroom of the dead markers, is what it is. What is the... Okay, this one must have been brought in from outside. ddx of the natural log of x is 1 over x.
So it would be 1 over...
So 1 over inverse cosine times the derivative of what's inside the parentheses. Inverse cosine of x. So chain rule says multiply by the derivative of what's inside the parentheses. So dy dx equals 1 over inverse cosine of x times, well, hopefully you've got it memorized. If I have it memorized, let's see. It's got a -1 in it because it has a co in it. So -1 over the square root of square root of what?
X squared. 1 minus x squared.
There we go. So that basically you could clean that up a little bit, I guess. -1 over, I don't know, just put it in a single fraction rather than 2. Maybe parentheses around that. I think that's about as simple as it gets. I would be content with the radical in the denominator. I wouldn't feel like the need to rationalize that because most of the time it's going to be irrational anyway. A, B, and C are similar to the one we just did in the notes with the 1 over x on the inside. So definitely be able to do any of those. Those hopefully aren't too terribly bad. So working our way backwards, 3.5. Let's see if any of these. 3.5. Do any of these look the least bit difficult? Oh, wow. Yeah, which one was just hideously ugly? 3 and 4. 4, I need to do an example. 4, I like 4 is kind of like a, oh, it's really nice. I like 4. So I'd put a star by that one. I don't draw really good stars, but I'm going to try maybe a gold star. There we go. So a star by that one. I like that one. Use implicit differentiation to do this. So this section was all about implicit differentiation. Here's a good example, which I don't remember if it really appeared in the notes or not, but we're all here talking about it. So, so let's see if we can do this. Y equals x to the sine x. Now this could maybe pass for a power function. If it were x to the 3rd power, you take the 3 and bring it out front, and then you say you reduce the exponent by 1. Doesn't work if we don't have a constant for an exponent. If there's a function of x for the exponent, it's not going to happen. So what we want to be able to do is use the properties of logarithms to get the sine x out of the exponent. And we can do that if we use... it says implicit differentiation, and although implicit differentiation does come into play, more specifically, it really should say this. Logarithmic differentiation. Because step 1 is take the natural log of both sides. That will enable us to get the sine x out of that exponent. So natural log of y equals the natural log of x to the sine x. Then we take the sine x and move that in front of the log. So the natural log of y equals sine x times the natural log of x. Now, no other way we can use properties of logarithms to simplify this, so we can go ahead and differentiate both sides with respect to x. d dx of the natural log of y equals d dx of sine x natural log of x. And you look at the expression inside the, I guess I should go ahead and take care of the left-hand side. d dx of natural log of y does involve the chain rule. Derivative of the natural log of something is 1 over that something times the derivative with respect to x of that something. So that takes care of the left-hand side. The right-hand side, we have a product. We want to find the derivative of sine x times natural log of x. So when we want to find the derivative of a product, what rule do we use? The product rule. So we've got to use the product rule, and it's going to be the first times the derivative of the second plus the second times the derivative of the first. It looks awful, but we're almost there, really. We have our dy dx, and to the extent that we're differentiating implicitly at this point, we'd want to isolate the dy dx on the left. All that takes is multiplying both sides by y, and so we get dy dx equals y times all of this, and not much really can happen. Sine x over x, maybe you could write. Sine x over x. But I don't know how you write natural log of x cosine x any simpler than that. In the final step, what could we do for the final step? What should we do for the final step?
X to the sine x. And for y.
Put in for y, x to the sine x. So x to the sine x times sine x over x plus natural log of x cosine of x.
Why do we have to do that for the last step?
You just like to have the right-hand side completely in terms of x. Since it was given explicitly in terms of x, we'd like to have the final answer explicitly in terms of x, dy dx explicitly in terms of x. So that's a fairly good example. I guess the downside of this example, if I'm presenting this as an illustration of implicit differentiation, once you take the derivative, there's only one dy dx. One key aspect of implicit differentiation is when you get to the stage where there were several terms that had y's in them, and so you have several dy dx's. You want to collect all the dy dx's, the expressions that have dy dx's in them on one side, factor out a dy dx, and then take that factor and divide both sides. So you're actually solving for dy dx and just multiplying both sides by y. It wasn't a really sophisticated example of that. I'm not going to ask you to find the second derivative using implicit differentiation. So 3b, if you took time to practice that, I think it was good. It enriched your intellect, but don't look for that on the test. I think one derivative using implicit differentiation will be adequate. Yeah, it really got kind of ugly, that second derivative, and I don't want you to feel like that's going to be expected of you on the test. I certainly don't want to feel like I have to grade it. So one derivative using implicit differentiation. Do you feel okay about 2 and 3a? Is that okay? And 2b is a nice follow-up question Here's a point on the graph. You found dy dx, so what's the slope of the tangent line at that point? This is probably not a function. It may not be a function of x at all, but the curve hopefully is smooth at that point. What's the slope of the tangent line there? You just substitute 1 for x and -3 for y, and that whatever expression that you got with x's and y's in it, and crunch that out, see what number you get. So hopefully that's a nice follow-up question. And definitely, I hope if A, B, and C aren't feeling good at this point, then the whole implicit differentiation process isn't feeling good. So hopefully that went well from those that we did in class that time. 3.4. 3.4. And let's see. I kind of need to look at all those. What's up there that could get left out in the cold? Which one? 8. Number 8. Let's see. Here we go. d dx of y, oops, sorry. That's implicit differentiation. Natural log of y equals the natural log of e to the x. So take the natural log of both sides. Simplify the right-hand side. Natural log of y equals what? X. Now, differentiate both sides with respect to x. d dx of the natural log of y equals d dx of x. On the left, as we usually do with logarithmic differentiation, we get 1 over y dy dx. On the right, d dx of x is 1. So we multiply both sides by y, and dy dx equals y, but what's y? So dy dx equals e to the x. So e to the x is kind of a cool function, because the slope of the tangent line to the graph at any point is equal to the y coordinate of that point. So the derivative of e to the x is e to the x. What's the second derivative of e to the x, do you suppose? E to the x. And the third derivative? E to the x, yeah. So it's kind of it's in a class of functions. It's not the only function that's equal to its derivative, but say a constant times e to the x would be what you're looking at if you're looking for a function that's equal to its derivative. So let's look at 6. 6 uses the chain rule. Like to do is this: insert new page and take all this and put it on that page. Maybe that's better. Get that out of the way. Now we do problem 6. Problem 6, if y equals e to the 7x, then dy dx equals, this is chain rule, this is the e to the x function composed with the 7x function. So this is derivative of e to a power is going to be e to that power times the derivative of that power. So the chain rule says multiply by the derivative of what's inside the parentheses, but what's inside the parentheses is basically that 7x. That's we're composing e with that 7x. So to multiply by the derivative of the inside function. So we multiply by the derivative of 7x, and so dy dx equals 7e to the 7x. And similarly with problem 7, if y equals e to the negative 5x squared, then dy dx equals e to the negative 5x squared times the derivative of negative 5x squared. So it's negative 10x e to the negative 5x squared. Just like that.
So I definitely need to put those in the test.
Yeah, they actually are kind of nice. I would hate to have omitted this from the test. They can get a little bit on the ugly side. 8 is basically the product rule. I can still do that if you'd like me to. Right. Now for one where there's kind of a product rule inside of the chain rule, 10 would 10 actually, or 11 would be a good one. E to the x tangent x dy dx there is going to be e to the x tangent x times the derivative of x tangent x. So we multiply by the derivative of the exponent. E to the exponent times the derivative of the exponent. And the derivative of the exponent involves the chain rule. So dy dx is going to equal e to the x tangent x times, how do we take the derivative of x tangent x?
You have to use the chain rule again.
Well, maybe not the chain rule, but which rule? It's x tangent x, so it's x times tangent x, so it's a product. So it's first times the derivative of the second derivative of tangent x, secant squared x. So this is the test where you want to have the derivatives of the 6 trig functions memorized, and you want to have the derivative of at least 3 of the inverse trig functions memorized, knowing you can get the derivative of the inverse functions multiplied by -1. So the first times the derivative of the second plus the second times the derivative of the first. Oops, what's the derivative of x? It's not x. Is 1. There we go. So can that be cleaned up at all? Secant squared x? I wouldn't think. I would think just maybe leave it like that. So, not a lot changes. So, and I guess if we didn't find the derivative of e to the x, we probably didn't find the derivative of 2 to the x either. Can you find the derivative of 2 to the x? This would have been problem 12. Again, logarithmic differentiation. Logarithmic differentiation. When there's a function of x in the exponent, that's a good place to go. So natural log of y equals the natural log of 2 to the x. Take the x and bring it out in front. Natural log of y equals x times the natural log of 2. Now when we differentiate both sides with respect to x, the right-hand side initially looks a little bad, but really it's not even a little bad. It's linear. X natural log of 2, if we graph y equals x natural log of 2, that's a straight line with the slope of log 2. So the derivative of that right-hand side is just log 2. You could use the product rule if you wanted to, but when you take the derivative of the natural log of 2, this is going to be 0. So a derivative of a constant times x is going to be that constant.
In the answers, you have 2 to the x ln 2.
Yes. Yes, we're almost there. 1 over y dy dx. The way I get that is I say dy dx equals y natural log of 2. And then we take that y, the original y was 2 to the x. So dy dx equals 2 to the x times the natural log of 2. And in general, the derivative of a to the x, where a is a constant, and let's see, I don't want a to be 0, and I suppose I prefer that it not be negative, and I'd rather it not equal 1. 1 to the x, straight as horizontal line. So it really needs to be a legitimate base of an exponential expression, an exponential function. So a needs to be positive and different from 1. If that's the case, this is going to be a to the x times the natural log of a. And in the special case, when a equals e, d dx equals e to the x, sorry, d dx of e to the x would be e to the x times the natural log of e. What's the natural log of e? 1. So that's e to the x. So if we had done that first, all we'd have to do is plug in e for a, and that would tell us that d dx of e to the x equals e to the x. I think some of these are easier than some of the other ones that we've done in some of these sections, so hopefully they would go well. So you say I did not provide solutions for 3 and 4. Well, 3a is just like problem 6. 3b is kind of like problem 7. 3c. It's kind of like 8, except that we didn't do problem 8. That's the product rule. And you just kind of take and put some things together. So e to the 2x sine 3x, let's do that. E to the 2x sine 3x, e to the 2x sine 3x, because you definitely want to see this one on the test. Dy dx, product rule, yes. We know how to find the derivative of e to the 2x. It involves a little bit of the chain rule, but we can do it. We know how to find the derivative sine of 3x. That involves a little bit of the chain rule, but we can do it. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So there's the product rule aspect. Dy dx equals e to the 2x times, okay, just a little bit of chain rule here. Derivative of sine of something is going to be the cosine of that something times the derivative of that something. Basically, it's 3 cosine 3x. That's the way that shakes out. Plus sine 3x, more chain rule. The derivative of e to a power is e to that power times the derivative of that power. So dread, is this really going to be 2 more steps and then probably shrink it down and then factor out a common factor? This is going to be e to the 2x times 3 cosine 3x plus sine of 3x times 2e to the 2x. Maybe factor out a common factor of e to the 2x. So dy dx equals e to the 2x times 3 cosine 3x plus 2 sine 3x. Kind of nice. Hate to leave that off the test. I might. But I hope I don't have to, because that's a good one. I think you could do that one. Anything else in the 3.4 list?
What about number 4?
Number 4. Which one? Which part? The B part. Yeah, that's where you want to exploit the properties of logarithms. Exploit the properties of logarithms to make that expression as nice as possible. Because if you just attack it with the chain rule and the quotient rule and product rule, it's a disaster. Unmitigated disaster. So problem 4, use the properties of logarithms. Make it as nice as humanly possible. F of x equals the natural log of x squared times 3x squared plus 7x plus 5 to the 1/2 minus the natural log of cosine 5x. So the log of the quotient equals the difference of the logs. Basically, log of the numerator minus log of the denominator. F of x, no derivatives yet. Log of the product equals the sum of the logs. Log of x squared plus the log of 3x squared plus 7x plus 5 to the 1/2. Can't really do anything with that cosine of 5x. Just kind of stuck with that. Natural log of cosine of 5x. And then the other thing to do before taking derivatives is take the 2 on the x squared, bring it out in front of the log, take the 1/2 exponent and bring that out in front of the log. So f of x equals 2 natural log of x plus 1/2 natural log of 3x squared plus 7x plus 5 minus, getting lonesome over here, cosine of 5x. Now, taking the derivative is not nearly as horrendous as it otherwise would have been. It would have been bad. F prime of x equals 2 times 1 over x. Just the constant multiple rule there. A little bit of chain rule here. It's going to be 1/2 times derivative of the natural log of something is 1 over that something times the derivative of that something. So 1 over 3x squared plus 7x plus 5 times 6x plus 7. Yeah? Minus, again, 1 over that something, 1 over cosine 5x times the derivative of that something. Now the derivative of cosine 5x involves the chain rule. It's going to be negative sine of 5x times what? Times 5. Negative sine of 5x times the derivative of 5x. So I have to multiply by 5. So f prime of x equals 2 over x plus 6x plus 7 over 2 times the quantity 3x squared plus 7x plus 5 minus, or maybe plus, it's minus what looks to be negative sine something, negative 5 sine something. So plus 5 sine 5x over, yeah. How about 5 tangent x? Can we do that? Tangent 5x. Yeah. 3.3. So I must have closed that window with a review on it. Get it back.
And that's the answer you want. You don't want us to do anything else.
I don't think so. There was back in the day when I would use WebAssign. WebAssign was actually very good. But in this particular case, I think they expected you to get a common denominator and to write all this as a single fraction. And I don't really see the point of that yet. At some point, maybe you want to set it equals 0, solve for x, define horizontal tangent lines, and all that. But I think this is far more elegant than the process that you would go through to get that common denominator. .3. Tell me these are easy. Yeah, I was hoping to get to an airplane problem today involving related rates. We'll see.
9
and 10. Let's look at 9. We'll probably save the airplane problem to the next test, but let's look at the ladder problem. And by probably, I mean definitely. Yeah. Definitely save the airplane problem to the next test. An 8-foot ladder leans against a wall at an angle theta with the horizontal. So there's the wall. There's the 8-foot ladder. There's the angle theta. 8 feet. Top of the ladder is x feet above the ground. So from there to there, that's x, like that. If the bottom of the ladder is pushed toward the wall, that way, find the rate at which x changes with respect to theta at the instant when theta equals 75 degrees. So I don't know how far the ladder is against the wall. It's push, 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 push. At some point, maybe theta equals 75 degrees. At that point, if x changes with respect to that, if theta were to increase by a certain amount, then what should we multiply that by? A certain number of radians, I guess I should say. What should we multiply that by to predict how much higher that ladder will go up on the wall? So basically dx d theta is what we're looking for. We want it in units of feet per radian, also feet per degree, because radian is such a darn large unit of measurement, 57 point something degrees. Feet per degree might be a little bit more useful. So can we write the relationship among the quantities x, theta, and 8 using a trigonometric function, perhaps? We have the side opposite theta, and we have the hypotenuse. So you think sine theta equals x over 8, just like that. we need dx d theta. So if we multiply both sides by 8, maybe switch things around a little bit, x equals 8 sine theta. So if we differentiate both sides with respect to theta, we can do this. dd theta of x equals dd theta of 8 sine theta. So dd theta of x equals dx d theta. That's what we want. That's what we need. dd theta of 8 sine theta, because the theta, with respect to which we're differentiating, matches the theta in the argument. There's no chain rule involved. It's just plain old 8 cosine theta.
Why wouldn't we do the product rule?
We could do the product rule. Constant multiple rule is a little bit simpler because when you do the product rule with the 8, when it comes time to multiply by the derivative of 8, that's going to be 0. And it's going to kill that kind of half of the product rule because we multiply by 0. Should totally try that a couple of times in lieu of using the constant multiple rule and see what goes on there. But at some point you realize, that's just going to be 0 times that, and you end up with just the 8 cosine thing. So the product rule will work, but constant multiple rule is shorter and sweeter in this case. So dx d theta when theta equals 75 degrees. Now, here's the thing. When it comes to calculating the cosine of theta, of a particular angle or particular number, it doesn't matter whether we say the cosine of 70 degrees or, 75 degrees is how many radians? Is that what it is? Dividing both by 15? Is it something over 12? Is it that? 5 pi over 12? Okay. That's what I was saying. It doesn't matter whether we take the cosine of 5 pi over 12 radians or the cosine of 75 degrees. Doesn't matter, just so long as the calculator is in the correct mode. If we want to find the cosine of 75 degrees, make sure the calculator is in degree mode. If we want to find the cosine of 5 pi over 12 radians, make sure the calculator is in radian mode. Either one will work. It's just that when we take this dx d theta, it's going to be expressed in units of whatever x is measured in divided by units of whatever theta is measured in. Well, x is measured in feet, and theta, when we're using the derivatives for sine and cosine that we established way back several weeks ago, theta is measured in radians. Always radians, never degrees. We'd have to have a factor of pi over 80, 180 over pi if we wanted to write that in terms of degrees. So, always radians. So it's going to be 8 times the cosine. I'm going to put in 75 degrees just because it said 75 degrees. But don't freak out. When we express the answer, it'll be in feet per radian. So, so it's calculator time. Got to make sure my calculator is in degree mode. Mode, degrees, second, quit. 8 cosine 75, enter. So 2.071, 2.071 feet per radian. Now, here's the thing. Once it gets to about 75 degrees, we're not going to push that ladder where the angle changes by another radian. That makes no sense at all. So it's going to make more sense if we say, well, if we were to increase, if we're pushing toward the wall, theta is increasing, right? So if we're going to increase it maybe to 76 degrees by pushing a little farther, we would expect the height up on the wall to increase by how much? How many feet? Well, not 2 feet, but if we convert this to feet per degree by multiplying 2.071, this is feet per radian. If we multiply by what? Pi radians for every 180 degrees, it's going to be 0.036. We can even throw in the 1, but I think the original information probably that's enough significant figures. 0.036 feet per degree. In that case, maybe inches per degree. Did I punch that up on the calculator correctly, you think? Did it look okay?
Normally it would be in parentheses, but since the radians is 1, it doesn't really matter for that.
Okay.
If radians was like feet per 2 radians, then you would need parentheses.
Right, yeah. So, does it seem okay? 0.036. And 0.036 is how many of a foot is how many inches? Whoops. So, if we're pushed on the ladder and so that we're from 75 to 76 degrees, we would expect that it would go up almost half an inch, 0.43 inches. Does that sort of make sense? That it could happen that way? Maybe possibly. So, ladder leans against the wall. Good problem.
It would go up 0.43 inches or 4 inches?
0.43 inches if we increase it. And I think what's interesting to do in a case like this would be to recalculate. Find the value of x. Find the value of x when theta is 75 degrees. So x equals 8 times the sine of 75 degrees. Figure out what that is. It'll be in feet. And then figure out the x sub 1, x sub 2 is 8 times the sine of 76 degrees. Find the difference and see if it's close to 0.43 inches. I guess initially we should see if it's close to 0.036 feet. You think it would be? 8 sine 76 minus 8 sine 75. Is that going to be close to 0.036? Because that's the difference in the two heights. Oh, got it. Not supposed to be exact, but it should be a good estimate of how much we're expecting that ladder to go up. So from 75 to 76, not quite that much, but close to it. So no airplane, but I think the ladder problem is a good problem.
Do you know how many questions will do this?
I do not. I'm sorry. I don't know exactly how many questions will be on there, but I just know you need to know the all those rules, product rule, quotient rule. Yes.
If you had to like pick any specific problems you specifically like off this homework, would you say all of them?
That I like.
Prefer like you know you.
I like this
certain
one.
Specific problems that you say we definitely need to know as far as. He's just doing the whole thing, of course, but like.
Let's see. What not to be missed. It's easier for me to point out the ones I don't like.
So many.
No.
So many.
I like problem 4, but I would say definitely don't use the quotient rule for that. Write that as 3 separate fractions. Problem 4 there. Write that as 3 separate fractions, and then each one is a number times x to a power, and use the power rule on each one. That's way better than the quotient rule. I think that's why I put it on there. I like 3 better than 5. If I had one good quotient rule to put on the test, it would more like 3, not more like 5. Not a very interesting numerator. I really don't like 1, although you do need to know the product rule. 1, there's just too much going on. It would make more sense to multiply it out. We did one in class where it was a polynomial. It would almost make as much sense to multiply that out, because you feel like after you go through the whole rigmarole of doing the product rule, you're gonna multiply it out anyway. So I don't like problem 1, but it doesn't mean don't memorize the product rule. Definitely know the product rule. And of course, scratch number 10, we just didn't have time to address that one. We'll see a similar problem when we do related rates. Unfortunately, not today, but soon. Anything else about the test? I would at least like to do the magic rectangle problem before we go today, but that's probably all I'm going to get to say about section 3.7. Anything else about the test? All right, so I think definitely the review, some significant proper subset of the review, and the test should be similar to it. Let's look at the magic rectangle problem. 3.7. Example 1. Imagine a rectangle with adjacent side lengths denoted by x and y, where the quantities x and y both vary with time. Well, let's not imagine. Let's say it's GeoGebra time. And let's see, I apologize if your name pops up here, but I think I have, let me at least stop recording here. There it is. Magic rectangle, basically, the length here, I want to say this dimension is, x, and this dimension is y of our magic rectangle. And as time passes, what happens? Let time pass. X and y both change. So let time go by, and x will increase and y will also increase. And the question will be, when x increases and when y increases, the area of the rectangle changes, yes? So if at any point in time we know what x is and we know what y is, we know how fast x is changing and how fast y is changing, could we answer the question, how fast is the area changing? That's the thing. We want to express a dA dt, the rate at which the area changes with respect to time, in terms of x, y, dx dt, and dy dt. So it's going to look something like this. We've got the area equals x times y. Rather than finding dy dx or dx dy, we're going to find everything, the derivative with respect to t. So I'm going to differentiate both sides with respect to t. ddt of a equals ddt of xy. And on the left, it's just dA dt. On the right, it's the product rule, x times y. We've got to find the derivative of that. So it's the first times the derivative of, differentiating with respect to t, the first times the derivative of the second plus the second times the derivative of the first. So dA dt is going to equal x times dy dt plus y times dx dt. So if you go to this rectangle and you tell me at some point in time a specific value of x, a specific value of y, the rate at which x is currently changing with respect to time, and the rate at which y is currently changing with respect to time, then I can substitute those values in here and tell you the rate at which the area is changing with respect to time. So just as the area is related to the side lengths, area equals x times y, the rate at which the area is changing is related to all four of these quantities. So what we have is related rates. The rates are related as well as the individual side lengths. So we've got a specific case. The specific case is this. At some point in time, x is 3 meters and y is 2 meters. And x is currently increasing at a rate of 0.2 of a meter per second. And we're just going to assume that's going to extend into the future as far as we can see, but all we know is the instantaneous rate. It's increasing at a rate of 0.2 of a meter per second. And y, dy dt, is also positive, so y is increasing at a rate of 1/10 of a meter per second. So we'll expect the length x to be a little bit more a second from now, and the height y to be a little bit greater a second from now as well. Just y is not increasing as fast. So how fast is the area changing with respect to time? Well, if we substitute these values over here, there's the x, there's the dy dt, there's the y, there's the dx dt. It's going to be 3 meters right there times 1/10 of a meter per second plus 2 meters right there times 0.2 of a meter per second. And evidently that's 0.3 of a square meter per second plus 0.4 of a square meter per second, which equals 0.7 square meters per second. So if we let maybe a second tick by, we would anticipate that the area would increase by about 0.7 of a square meter. Now, the actual amount is a little bit more if we assume that that dx dt is a constant, dy dt is a constant over the next second, because x and y themselves are increasing with respect to time. So just for a moment, consider what happens if we go into the future. I guess I could run the animation. Let's see. Will it go? Yeah, there we go. I need to see how to make the cells on the spreadsheet a little bit bigger and a little bit more visible. I've got dx dt at a constant 0.2 of a meter per second and dy dt at a constant 1/10 of a meter per second. dA dt is increasing throughout this time interval because it depends on x and y, and x and y are increasing throughout this time interval. So look at what the area is 1 second from now. We had anticipated that it would be, well, that it would increase by 0.7 of a square meter. It actually increased by about 0.72 of a square meter, from 6 to 6.72. A smaller time interval might have worked this out a little bit better for us, and rounding. What? Maybe it was giving me. Maybe it's giving me as many decimal places as as necessary there. But if we're at a particular point, suppose we're at 2.5. T equals 2.5 seconds into the future, and we're wondering what the area will be a second from now. Well, according to the spreadsheet here, can you read that tiny number right there? 0.8. According to the spreadsheet, the area is increasing at the rate of 0.8 of a square meter per second. So what's our best guess as to what the area will be 1 second from now? Would this make sense? 5, 7, 6, 8.675. That's probably a little bit more than that because x and y are increasing 8.675. So what will it be at t equals 3.5? 8.675, maybe a little bit more. 8.695. But a fairly decent estimate. The estimate gets better as we go with smaller time intervals. If it's currently increasing at a rate of 0.8 of a square meter per second, what's your best guess as to what it will be 1/10 of a second from now? 1/10 of a second from now. Eight tenths of a square meter per second in 1/10 of a second. We'll add what? Would that make sense? In 1/10 of a second? What's this? Did I do that right? 7.955? Okay, 1/10 of a second. There we go. So it's a pretty good predictor of what's going on there.